A spherical thermocouple junction of diameter 0.706 mm is to be used for the measurement of temperature of a gas stream. The convective heat transfer coefficient on the bead surface is 400 watts per meter square Kelvin. Thermophysical properties of thermocouple material are K is equal to 20 watts per meter Kelvin, C is equal to 400 joule per kg Kelvin, and rho is equal to 8500 kg per meter cube. If the thermocouple initially at 30 degrees centigrade is placed in a hot stream of 300 degrees centigrade, then time taken by the bead to reach 298 degrees centigrade is A 2.35 second, B 4.9 second, C 14.7 second, D 29.4 second. Now it is the problem of unsteady state or transient heat conduction. The solution to the problem is given like this. We see the bead size is 0.706 mm. Diameter of the bead is given. Therefore, D is equal to 0.706 mm of very small size. The convective heat transfer coefficient is given from the bead surface as H is equal to 400 watts per meter square per Kelvin, and the conductivity of the thermocouple material K is equal to 20 watts per meter Kelvin, and the specific heat is 400 joule per kg Kelvin. Density is given as 8500 kg per meter cube. For the lumped heat capacity analysis, where internal temperature gradients are negligible, the criteria is Biot number should be equal to Hs by K. First of all, let us calculate the value of Biot number. If it is less than 0.1, we can take it granted that lumped heat capacity analysis is valid, and hence the temperature of the body would now be a function of time alone. So first of all, let us calculate the Biot number. H into V by A divided by K, where V is the volume and A is the surface area. H into what is the volume? 4/3 pi r cube divided by 4 pi r square into 1 by K. It results in H into r cube by r square. It results in r by 3 into 1 by K, where H is given as 400, R is 0.706 divided by 1000 divided by 2 into 1 by 3, where K value is given as 20 watts per meter square Kelvin. Since it is much lesser than 0.1, lumped heat capacity analysis is valid. Now, writing the temperature as a function of time, because lumped heat capacity analysis is valid, that is Ti minus T infinity divided by T minus T infinity. Now he has given the initial temperature of the stream is initial temperature of the body. Initial temperature of the thermocouple is given as 30, and fluid temperature is 300 degrees centigrade, and T is given as 298 degrees centigrade. This is equal to e to the power of HA by rho Vc into tau. It results in 298. I could write this as 298 minus 300 divided by 30 minus 300 is equal to e to the power of minus HA by rho Vc into tau, where tau is the time taken by the thermocouple junction to reach a temperature of 298 degrees centigrade. Everything else is given here. A is 4 pi r square, volume is 4/3 pi r cube, H is also given, specific heat capacity is 400 joule per kg degree centigrade, implies the time taken by the thermocouple junction would obtain as 4.9 seconds. Hence the problem. B is the answer. Now I shall solve a problem in GATE 1998. The temperature variation under steady state across a composite slab of two materials with thermal conductivity is K1 and K2 is shown in figure. Then which one of the following statements holds. The figure is given like this. This is TA, this is TB. This is the direction of heat transfer, K1, K2. The answers are given like this. K1 is greater than K2. K1 is equal to K2. K1 is equal to 0. K1 is less than K2. Here the solution could be given like this. Q is given as minus Ka dt by dx. A is same throughout, Q is also same throughout, therefore Q by A is equal to minus K into dt by dx. Minus sign is only meant for that as x increases, this is the direction of x, the temperature is decreasing. But for that there is no significance of minus. Minus is there only to satisfy the Clausius statement of second law, which says that heat always flow from high temperature to the low temperature. Because since dt by dx is more in a first slab, that is slope of temperature drop is higher in slab 1. For the same Q by A, K1 is lesser than K2 is very clearly given. The slope is greater. The slope dt by dx is greater in the first slab as compared to the second slab as seen in the figure. Therefore, K must be lesser in the first slab. Hence the problem. Now I shall solve a problem given in GATE 1996. For a given heat flow, and for the same thickness, the temperature drop across the material will be maximum for A, copper, B, steel, C, glass wool, D, refractory brick. The solution is given like this. For the same thickness B, if A is the area of heat transfer, Q, Fourier law states that Q is equal to minus Ka dt by dx, where K is conductivity. Where K is conductivity, if K is minimum, then dt by dx or temperature drop is maximum. K is minimum. If you arrange the above materials in the descending order of conductivities, K of copper is greater than K of steel, is greater than K of refractory brick, is greater than K of glass wool. Since K is least in the glass wool, temperature drop is a maximum. Answer is C. K is least for the glass wool, Hence the temperature drop across the glass wool slab is maximum for a given temperature drop or delta T across the slab. Hence the problem. Now I shall solve a problem given in GATE 2007. The problem is given like this. The average heat transfer coefficient on a thin hot vertical plate suspended in a still air can be determined from observations of the change in plate temperature with time as it cools. Assume the plate temperature to be uniform at any instant of time and the radiation heat exchange with the surroundings negligible. The ambient temperature is 25 degrees centigrade. The plate has a total surface area of 0.1 meter square and a mass of 4 kg. The specific heat of the plate material is (2.5 kilojoule per kg Kelvin). The convective heat transfer coefficient in watts per meter square Kelvin at the instant when the plate temperature is 225 degrees centigrade and the change in plate temperature with time dt by d small t is minus 0.02 Kelvin per second is A 200, B 20, C 15, D 10. The solution to this problem could be given like this. Thin hot vertical plate is suspended in air. The plate temperature is uniform, therefore temperature is same everywhere in the plate. The temperature is given at the instant of a certain time, 225 degrees centigrade. The fluid is at a temperature of 25 degrees centigrade. This is plate. There is a convection heat loss from the plate to the surrounding ambient fluid. At the instant when the plate temperature is 225 degrees centigrade, writing the energy balance or first law of thermodynamics, the rate of fall of internal energy of plate is equal to rate of convective heat transfer from plate to fluid, that is mCp dt by dt is equal to H A total surface area into temperature of the plate minus temperature of the fluid. The mass of the plate is already given as 4 kg. 4 into specific heat is given as 2.5 kilojoules. Let us convert into the joules. dt by d tau dt is given as, minus is only significant that rate of decrease there, minus is already there, minus 0.02. Minus sign only indicates that it is the rate of decrease in temperature. H we do not know. Surface area of the plate total is 0.1. Temperature of the plate is 225 minus 25. Therefore H is equal to 4 into 2.5 into 10 cube into 0.02 divided by 0.1 into 200. So many watts per meter square Kelvin. Here also lumped heat capacity analysis can be assumed to be valid because in the problem it is given that the temperature is uniform throughout. Hence Biot number, even if we calculate the Biot number for the plate, it would happen to be less than 0.1, making sure that lumped heat capacity analysis is valid. Hence the problem. Now I shall solve a problem in GATE 2007, that is linked answer questions. Given for 4 marks. The problem goes like this. Consider steady one-dimensional heat flow in a plate of 20 mm thickness with a uniform heat generation of 80 megawatts per meter cube. The left and right faces are kept at constant temperatures of 160 degrees centigrade and 120 degrees centigrade respectively. The plate has a constant thermal conductivity of 200 watts per meter Kelvin. Now the question is given like this. The location of maximum temperature within the plate from its left face is A 15 mm, B 10 mm, C 5 mm, D 0 mm. And another question that is given along with this is the maximum temperature within the plate in degrees Celsius or centigrade is A 160, 165, 200, D 250. There is a plate of uniform thermal conductivity. Plate thickness has been given as, I can take it as L, 20 by 1000 meters. On the left face, I consider this as X is 0. On the right face, X is plus L, that is 0.02 meters. This is left face. Temperature at left face, that is at X is equal to 0, is given as 160. Temperature at X is equal to L is given as 120 degrees centigrade. Conductivity K is uniform throughout, and there is a uniform heat generation given in megawatt per meter cube, or which could be converted to watt per meter cube. Q dot is equal to 80 megawatt, 80 into 10 power 6 watt per meter cube. Conductivity of the slab is given as 200. Maybe it is aluminium. Writing the differential equation, we get d square T by dx square plus q dot by k is equal to 0, assuming that it is one-dimensional and steady state. Assuming one-dimensional steady state with heat generation. Therefore, d square T by dx square is equal to minus q dot by k. dt by dx is equal to minus q dot by k into x plus C1. Temperature is minus q dot by k into x plus C1x plus C2. So we need to calculate C1 and C2 from the two known boundary conditions at x is equal to 0 and at x is equal to L. Put x is equal to 0 implies temperature is 160 is equal to minus q dot by k into 0 plus C1 into 0 plus C2 implies C2 is 160. Put x is equal to 0.02 meters, that is 20 mm, implies 120 is equal to, at x is equal to L, temperature is 120, minus q dot by k into this is x square by 2, q dot k into x, q dot by the temperature after integrating x square by 2, this is 0 square by 2. Please correct that. When you integrate dt by dx is equal to minus q dot by k into x plus c1 on both sides, we get temperature is minus q dot by k into x square by 2 plus c1x plus c2. 0.02 whole square by 2 plus c1 into 0.02 plus c2, what we get as 160. Putting the values of q dot and k, we will get the value of c1. After getting c1, now to get the location where the temperature is maximum, when the temperature is maximum, dt by dx is equal to 0 implies minus q dot by k into x plus c1 is equal to 0. Having known c1 and q dot and k, immediately we can get x, that is the location where the temperature is maximum. It is the location where T is maximum. We will obtain in meters. That is the answer for the first question. How much is the maximum temperature? What is the T max? To get this, put x in, put x value in temperature is equal to minus q dot by k x square by 2 plus c1x plus c2, because we know c1 c2, we know q dot, and put the value of x in the equation where that we already got that where the temperature is maximum. This is the location where the temperature is maximum. Put that x value in the temperature function, we will get the T max. Hence the problem.